In 1752, Benjamin Franklin performed one of the world's most renowned experiments by flying a kite into a thunderstorm to attract a lightning bolt. This was to prove that lightning was an electric fluid and would behave similarly to other fluids. But it wasn't just Franklin who made progress into discoveries in the study of electricity. Boyle, Volta, Oersted, Ampere, Faraday, Ohm, Maxwell, Bell, Edison, Siemens and Tesla were also some of many scientists who helped shape the common understanding of the interesting phenomena which is an integral part of our modern society today. Electricity is a mode of transferring energy via charged particles moving through conductive materials. Charged particles also behave in a unique way when they are placed in an electric field.
It was a physicist from the French military, Charles Augustin de Coulomb, in 1785, who declared that an amount of charge flowing through a circuit would be denoted 1 ampere of current, multiplied by the length of time elapsed. Charge was later renamed to be measured in coulombs, to honor Coulomb's work. A coulomb of charge is defined as 1.6 times 10 to the power of 19 electrons. A charged particle, also known as an electric charge, can be of positive or negative nature. All charges are built up of combinations of the elementary charges, protons and electrons. Every object has a net charge. If the number of positive and negative charges are equal, the object is said to be of neutral or no charge. If the net charge is negative, there are more electrons present in the object than protons. Conversely, if there are more protons than electrons in the object will have a positive net charge. Coulomb's law states charged bodies will exert a force on each other.
Coulomb's law states that charged bodies will exert a force on each other, with such a force being proportional to the size of both charges and Coulomb's constant, denoted K subscript C, while also being inversely proportional to the squared distance between the two charged bodies. Mathematically, the formula reads force equals Kc Q1 Q2 divided by R squared. Fields are a region of space around a particle or object in which other objects will experience a force. Electric fields are regions in which charged particles will experience a force generated by other charged particles. Electric fields extend away from positive charges and towards negative charges. Electric fields can be arbitrarily represented by field lines. By convention, the greater the density of field lines implies the greater electric field strength in that region. When a charged particle is placed in an electric field, it will exert and experience a force due to the central charge. This force can be used to find the electric field strength at that location by dividing the force at which the test charge experiences divided by the charge of the test charge. The locus of points which experience the same electric field strength are said to be equidistant from the central charged particle. When there is more than one charged particle in a system, every point on the plane will have a resultant electric field strength and direction. Each point of this field is a vector. Thus, the resultant field strength at any point is calculated via vector addition. When an electric field goes through a surface, or plane, the surface is said to have electric flux. Electric flux is a measure of the amount of electric field going through a given surface. Electric flux, similar to electric fields, can be arbitrarily imagined as the number of electric field lines going through a surface. As previously mentioned, the larger the amount of electric field that passes through a surface, the larger the amount of electric flux of the surface.
Thus, the relationship can be represented by the equation phi equals Ea cos theta, where the Greek letter phi denotes the total electric flux passing through the surface, equaling the product of the surface area and the amount of electric field passing through the surface area and the cosine of theta, where theta is the equivalent to the angle made between the direction the surface is facing and the direction of the field lines. During 1813, German mathematician Carl Friedrich Gauss discovered a method of finding the electric flux of any plane or container surrounding a charge. It is now known as Gauss's law. Gauss's law states that the total flux of a 3D object is defined as the sum of the electric charge contained in the object divided by the permittivity of space. To make the process of using Gauss's law cleaner, in 1, 2, and 3 dimensions, Gaussian surfaces were assigned. A Gaussian surface is a closed shape in 3-dimensional space. It was determined that the most effective shapes to use to enclose charges are cylinders and spheres. These shapes are most effective as their surfaces are equidistant from the charges, and the field lines passing through the surface are going the way the surface is facing. Such an equation works because a Gaussian surface can have the properties to enable the following derivation. If you take an infinitesimally small point of the surface, also known as the tiny change in area denoted dA, you can calculate the electric flux that passes through such an area via Ea cos theta, where theta is 0 degrees as the surface is facing the same direction as the field lines radiating from the charged object. Therefore, cosine theta equals 1. Furthermore, if we cover up the entire surface in these smaller areas, we can add up all the areas and give the corresponding values of electric flux to give the total flux passing through an object. This can be done by using an integral of the size of the electric field going through each area multiplied by the electric flux passing through one of the infinitesimally small areas dA. As electric field strength is the same at each point due to the Gaussian surface being equidistant from the charge, the variable E becomes a constant value for electric flux in each small region. Thus, we can also take the variable E out of the integral and complete the integration to find the total flux of the Gaussian surface. The electric field strength can be found by using simultaneous equations on the derived equation and Gauss's law. The result from Gauss's law can be applied to find the electric field strength at any distance from the charge. A great example is the electric field strength at any distance from the plane of infinite size which has uniform charge. Think of it as a sheet of charge that can extend infinitely in any 2D direction, similar to a Cartesian plane. This plane is infinitely thin, tall, and wide, and has an even distribution of charge over its surface. It should be noted that the plane is non-conductive, meaning that charges cannot move around and create abnormalities in the uniform electric field which it emanates. The charge density of our infinite plane is denoted by sigma. As the plane is flat, the electric field lines will be perpendicular to the plane as well because the plane is infinitely large. Electric field lines will evenly distribute themselves by stretching outwards towards infinity and will never curve. By using a cylinder as our Gaussian surface, the ends of the cylinder will be equidistant on either side of the plane. Upon cancelling out the variables, we find that electric field strength is not reliant on the distance from the plane but rather the charge density of the plane.